When we're dealing with AC loads in our photovoltaic systems, we're going to need a device called an inverter. That's going to help us convert from the natural DC power that we generate with the modules and store in our batteries, and converts it into alternating current, or AC current, to run the AC loads. There's different types of inverters, there's different output forms. We have to get concerned about things like efficiency and so on. So during this segment, we're going to cover some of the various factors that are important when we deal with inverters. Some of the main factors that come to mind are the surge capability of the inverter, or the output versus time, the ability of that inverter to meet load demands at different levels for different amounts of time, the efficiency of that inverter in terms of converting DC energy into AC energy, and the output waveform. Is it a squarish type of form? Is it a sinusoidal type of form? And so on. First thing we want to look at is the power rating of the inverter. It's got to be able to deliver the energy that you need to run perhaps all the AC loads that you might have added up in your system. The problem with inverter power ratings as of now, hopefully this situation will change in the near future, but one of the problems is there's no standard period of time for rating inverters. One standard that's emerging is a rating system that makes a lot of sense, and that's a continuous rating. How much power can the inverter put out if it's just continuously operated for hours and hours? But that's not always the way that inverters are rated. Some use a continuous rating. Some rate themselves for how much power they can put out over 30 minutes. Some, how much power they can put out over 15 minutes. The important thing to realize is the output power of an inverter depends on time. There's heat generated, and the inverter can only operate with so much heat for so much time. The time of operation decreases with temperature. The hotter the inverter, the shorter period of time it can operate before it shuts itself down. Most inverters are rated at operating at 25 degrees C. Some are rated at 20 degrees C. Some are even rated at 40 degrees C. The point is, you've got to know the details of how the rating is made in order to compare apples to apples. If an inverter operates at a higher temperature, the power that you get will be less. The amount of time that you have to operate that inverter will be less. An inverter, just like a person, gets too hot and too tired and internally shuts itself down if it operates at too high of a temperature. Ideally, I think the best ratings for inverters would occur if the power rating was a continuous rating and the temperature rating was at 40 degrees C. The reason for this is this gives you sort of the maximum limits as to where that inverter would operate. Your performance is probably going to be better because you could operate the inverter for less than a continuous amount of time and get a little more power from it, and you probably would operate it at lower temperatures than 40 degrees C. Although, when an inverter is up and running at a steady state power, its internal temperatures can rise quite high. The point is, look very carefully at inverter literature to find out exactly what it says about how it's rated, and therefore know a little bit more about how it might operate under your conditions. Let's take a look graphically at how we might look at power versus time. Some inverter literatures give you this information, some do not. They may simply give you one or two printed numbers, and you have to guess in between. The best approach, I think, is to have a nice graphical presentation of power versus time. What you notice in general for all manufacturers is that for a long amount of time, you get a certain continuous rating of output power. Over a shorter period of time, you can extract more power from that inverter before it shuts itself off. This graph that we show, for example, shows that on a relatively continuous basis, or more than 60 minutes, you might get a little less than 2,000 watts from this inverter. At roughly 30 minutes, you would get 2,000 watts. So this is called a 2,000 watt inverter. It happens to be rated at the 30-minute rating. And for a shorter period of time than 30 minutes, let's say 5 minutes or 10 minutes, you can get 4,000 or 5,000 watts from this same inverter. That's nice, because that means that you can operate some large loads for a short amount of time, large compressors, heavy motors for a short amount of time, and yet have a 2,000 watt inverter designed to handle your continuous loads. So if you can try and obtain manufacturer's literature for load power versus time, not just one number. What you might see in the literature might be power output, 2,400 watts for 30 minutes. Well, what is it for less than 30, and what is it for more than 30? Try and get more detailed information if you can. The second important factor that we need to consider with inverters is their efficiency, their ability to convert DC energy in into AC energy out, or DC power in into AC power out. Again, many manufacturers will give you one number. What you typically would like to look at, though, is a graphical representation of efficiency over different load levels. What you want to do is examine the output efficiency of an inverter compared to power, watts or kilowatts. We have a representation of a couple types of technology. In the past, inverters were made with silicon-controlled rectifiers, or SCRs. These used up a lot of power themselves, so the efficiency curves tended to simply drop down in efficiency on a steady basis as you decrease the amount of load that was being used, because more and more of the parasitic losses were showing up. But now we have transistorized-based inverters, and the efficiency curves are quite good. In fact, they actually peak in their efficiency at very low levels of power, and then slowly drop off in power as you increase the amount of power demanded. The point is that you can count on an inverter nowadays that has a fairly high and fairly flat efficiency curve over most of its range. What this means is that inverters nowadays are good for operating small loads as well as large loads. You might have a 2,000 watt inverter and still be able to operate a 100 or 200 watt load with relatively high efficiency, not worry about losses in that case. In general, we can compare different types of inverters and say that there's general differences in their efficiencies. This isn't always true, and as this tape becomes aged, perhaps different inverters will improve in their efficiency more than I predict. But in general, we can draw a distinction between sine wave inverters and modified square wave, what often are called modified sine wave inverters. In general, the modified square wave inverters tend to be more efficient over most of their range. The sine wave inverters, although they produce a nice sinusoidal output, because of filtering and electronics inside, tend to operate at slightly lower efficiencies. But I say this with a word of caution. I can draw that distinction today, but even today I might be able to compare two types of inverters, in this case a sine wave inverter and a modified square inverter, and their efficiencies are comparable. In the future, perhaps sine wave inverters will become even more efficient. So it's important to be able to draw distinctions at one time, but watch out in the future. Technology may improve and the efficiency ratings of these inverters may change. Let's take a look at some different output waveforms from inverters. This would be the third important characteristic of inverters. Not only do we have to know how efficiently they convert power and what kind of power they can deliver for what amount of time, but we have to know the form of the AC output. Is it a smooth sinusoidal output? Is it a steppy kind of output, or what? This might be important in terms of matching up an inverter to different types of loads. In general, we can talk about three different types of output waveforms. Let's take a look at those now. The simplest type would be what you could call a square wave output. Simple plus voltage, minus voltage, plus voltage, minus voltage. Graphically, I can show it here as a nice clean square wave. But electronically, a square wave is actually made up of an awful lot of different types of waves at different frequencies. We call that the amount of different frequencies added together, the harmonic distortion that's output from the inverter. The typical harmonic distortion output from a square wave inverter is quite high. It's greater than 40%, 50% or more. These types of inverters might be useful for operating simple resisted type loads, heaters, toasters, small electric devices that might operate for a short amount of time. Their efficiency tends to be fairly low, 60 to 80% or less, and they also tend to have poor surge capability. They can surge maybe 10% or 20% above their peak rating. So a square wave type of inverter would be useful only for very small loads for very short amounts of time or for purely resistive loads. In general, I don't recommend square wave inverters for photovoltaic applications. Typically, we're dealing with loads that are delicate enough and important enough that you need to step up to another type of inverter. Another type of inverter output waveform that we want to consider is what's often called modified sine wave or modified square wave. An example might be this hard interface Freedom 20. The terminology of modified sine wave to me is a little bit of marketing manipulation. I would rather call it a modified square wave. It gives more of a sense of what you really get from the output. But these types of inverters are widely used worldwide in photovoltaic applications. There's a lot of reasons for that. They come in moderately low cost, quite affordable. The harmonic distortion now is much less than that square wave type of inverter, maybe 20% or less. That's pretty much acceptable for a wide variety of AC types of loads and appliances that we might use. They come with relatively good efficiency, typically greater than 90% over much of their range, with real good surge capacity as well, maybe 300% or more surge capacity above their normal rating. They're able to operate a wide variety of applications. The waveform shape itself is kind of an interesting thing to look at. There's a delay through zero, then a positive pulse, then a delay through zero, and then a negative pulse, and that repeats. That's where I get the term modified square. You can see that you can sort of imagine a sine wave curve going through this, and it sort of approximates the sine wave. But I think it's more appropriate to call it a modified square. This type of output is designed into a device that's of good cost, excellent efficiency, and can operate a wide variety of applications. So we find it being the inverter of choice in many cases around the world. The third type of inverter output waveform we should talk about is pure sinusoidal waveform. An example of an inverter that produces that might be this Trace 4,000 watt sine wave inverter. Now we're dealing with the expected sort of pure sinusoidal waveform that we get from utility power. So all types of electronic devices, delicate electronics and radio equipment and so on will operate just fine from the output from sine wave inverters. Some of the characteristics of these inverters are very low harmonic distortion, typically less than 5% now, maybe 4 or 3% total harmonic distortion. In general, sine wave inverters cost a little bit more per watt than modified square inverters, but that may not always be true. The cost of inverters is very dynamic right now, and I would watch for the cost of sine wave inverters to come down. The efficiency of the inverters, in general, tends to be a little less than modified square wave inverters, in the 80 to 90% range, as opposed to, in general, above 90% for modified square inverters. But that also is changing in the 90s. So I would be very careful to keep my eye on new developments with sine wave inverters, because certainly, given a nice, pure sinusoidal waveform, is much more gentle and to be expected by all of your loads, both mechanical, electromechanical, resistive, and electronic. So the choice of using a sine wave inverter or a modified square wave inverter is up to you. It's not a choice of black and white. I know of a wide variety of loads that can operate both off of modified square wave and sine wave. If you have delicate electronic equipment, radio equipment and so on, you may be restricted to using only a sine wave type of inverter. However, you may find that a wide variety of appliances or electronic loads have some sort of power supply built in. They're going to take the AC power anyway and rectify it into some sort of DC power inside the device. The quality of that power supply that's built into your load will determine whether a modified square wave or a sine wave inverter is going to be acceptable. When we're dealing with system design, we have to look at inverter sizing. Not physically the size of the inverter, but how many kilowatts continuously can the inverter put out? Also, how much can it surge? The concerns that we have are that the inverter meets all of the loads that might be on at the same time for minutes or many, many hours. That would be the continuous rating of the inverter. For example, here we have a 2,000 watt inverter. Here we have a 4,000 watt inverter. Continuous rating. You've also got to choose an inverter that can surge enough to start your motor loads that might come on. The calculation should include all of the loads that might be on at one time, and then add to that the surge requirement of the heavy motor loads. And keep in mind that things like compressors on refrigerators or motors for water pumps can surge 5 to 6 times their normal rating for a few seconds. And the inverter must be sized to not only handle the continuous load, but supply that surge as well. Once you've chosen an inverter to meet your continuous and your surge requirements, you are given by the manufacturer's designing process the input DC voltage. It puts out, let's say, 110 or 220 volts AC, but what's the DC voltage that you put in? Is it 12, 24, 36, 48, 120? That comes from the inverter manufacturer's choices. You may get a range. You may, for example, get a 1,000 watt or 2,000 watt inverter that comes with both 12 and 24 volt choices. Or you may simply be given an inverter that comes with a certain restricted value, like 12 or 24 or 48 volts. For example, in the trace example here, this 4,000 watt inverter comes both 24 and 48 volts input. So in your process of doing your calculations, that's why you must add up your AC loads, then stop, choose an inverter, and once you've chosen the inverter based on continuous output and surge capability, then you can proceed with your calculations, because now you know the input DC voltage to that inverter. And that's going to determine the DC voltage of your array and your battery. There's another type of inverter that I want to mention before I close. That's a utility interactive type of inverter. A design of an inverter that can send power out to utility and draw from the utility at night. Typically, utility interactive inverters involve no batteries. We have systems that involve photovoltaic arrays connected to the inverter, then that's connected to the house and to the city power. No batteries, no charge regulators, and so on. The utility supplies the power at night because the modules don't work at all. The utility is like the big battery that you can rely on anytime. All of these inverters are true sine wave inverters, putting out a waveform that has less than 5% total harmonic distortion. And they also synchronize with the utility waveform itself, so that the power can go from your photovoltaic system or can feed into your photovoltaic system. A downfall of these utility interactive inverters is that since they are interacting with the utility all the time and sending power into the utility line, if the utility power shuts down, the inverter shuts down, and your photovoltaic system typically shuts off. So a choice of a true utility interactive inverter would only be made in those cases where you have a reliable utility grid. Not appropriate to have a utility-dependent system where you've got brownouts and blackouts threatening you. But in cases where you have a stable and good utility system feeding into your system, you can install modules, a utility interactive inverter, and create what we called in the past demand-side management capabilities, where you were able to reduce the load that is seen by the utility, and you reduce your daily energy requirements from the utility, thereby reducing your monthly bill. In photovoltaic system design, one of the critical components that we need to be concerned with is charge regulators. We're not dealing with voltage regulators that somehow keep our voltage range within a certain set of limits. We're talking about a device that controls the amount and the flow of current from the solar modules into our batteries. Similar to a car or any other situation where you've got a charger that possibly could overcharge your batteries. A simple charge controller simply does that one function, controls the charge flow and either reduces it or stops the flow altogether when the battery gets too full. Other functions that can be built into the charge controller or system controller, if we have something more complex, might include preventing the batteries from being over-discharged. So instead of preventing the battery from being overcharged by the array, other components in the electronics could watch that battery voltage, and if our loads are operating too much or if the weather has been bad for too long and the battery state of charge is getting too low, perhaps the device will disconnect some non-essential loads. So we can protect the battery both from being overcharged and from being over-discharged. Other functions that might be built into our charge regulation center or component might be some sort of feedback to the user. It's at this component where we're measuring array current and battery voltage. That should be indicated to the user, at least battery voltage. So some sort of light or simple dial or maybe even a digital meter would be involved at this point. Another function of charge regulators might be to divert solar power away from our batteries when the batteries are full. One common configuration is simply to diminish or stop the charging and leave the battery the way it is. But we have perhaps afternoon power being developed by the array. Some regulators can use that power. They simply turn a switch and divert that power to another auxiliary load. And finally, another function that we might make use of with these devices is as a central wiring center, a place where the array wiring, the battery wiring, perhaps our inverter wiring, all might come together in one central unit. So again, as with many of our other components, we have a lot of flexibility in terms of the size and the complexity of what our charge regulators might be doing for us. Let's take a look at some of the different possible configurations of charge regulation in photovoltaic systems. One of the basic or the simplest ways of involving a charge regulator in a PV system is to install the charge regulator between the photovoltaic array and the battery. This way, the series design of regulators or shunting type of regulators cuts off array power when the battery's full. The power to the load proceeds from the battery. It's not really passing through the regulator at this point. Remember, the regulator is simply preventing the array from overcharging the battery. Another approach or another variation of this same idea is to have your charge regulator between the photovoltaic array and the battery. But now it's designed to be able to divert excess power away from your batteries once they're full to some sort of auxiliary load. The important thing here is that this auxiliary load is getting unregulated power. It's directly connected to the PV array. So it can't be any sort of electronic device, but typically this might be some sort of heater, maybe a water heater. It might be a water pump for pumping water up into a tank. It might be a ceiling fan or other type of simple motor. Another type of regulator configuration involves having the charge regulator not between the photovoltaic array and the battery, but between the battery and some sort of dedicated auxiliary load. In other words, your photovoltaic array current flows into your battery all the time. As the battery becomes more and more full, the current regulator begins to shunt this power away from the battery to the auxiliary load. So in this case, the auxiliary load is not an option. It's mandatory in this case. The nice thing about this type of configuration is that you can connect a number of different renewable energy sources to your battery bank. Wind power, mini hydro, photovoltaic arrays. All of that current can go directly into the large battery bank, which can absorb that current. And then as the battery gets too full, it simply begins to divert current away to that auxiliary load. For larger and larger systems, we may not be able to simply use one large charge regulator that can handle all the array current. We may choose instead to put in multiple charge regulators that handle subarrays, small sections of our total array. In this case, for example, we show 3 charge regulators handling 3 small subarrays. Each one of these charge regulators then combines in its output and feeds the current into our battery. The set points of these charge regulators do not have to be exactly the same. They don't have to be synchronized in any particular way. In fact, we often deliberately set the voltage point at these charge regulators at different levels to allow different amounts of current to be cut off as the battery reaches full state of charge. In this way, we can use a simple on-off type of regulator, but with multiple regulators, we effectively get multiple gentle stages of cutting down of our charging current. Let's look at 3 basic different types of electronic designs for charge regulators. First type we might want to consider is the basic shunt type of regulator. In this case, the array is connected through our charge regulator to our battery bank. When the battery starts to become too full, the modules are then shunted. They're short-circuited. We can do that with photovoltaic modules. There's no danger at all and no damage to the module. So the modules are operated at their short-circuit current. 0 voltage, maximum current flow simply looping in the module. The advantage of this type of shunt regulator design is that the regulator is very simple and typically in low in cost. The disadvantage, though, is that in the shunting process, when the power is being shunted away from the battery, it's generating heat within the regulator itself. So that causes some physical limitations in terms of the size and economical design of these types of charge regulators. So typically, they're limited in their currents, maybe up to 20 amps or so. So these types of regulators are typically found and used in simple, small types of systems. An example of a small type of shunt regulator might be this type of design, a 10 amp shunting type of regulator. The array and battery wires are connected to the shunt regulator, and so might be the loads as well. When the battery reaches too high of a voltage, the power of the array is shunted within the regulator itself. So in this case, when the battery reaches too high of a state of charge, the array circuit is open. So the regulator now operates the modules at open circuit voltage, not short circuit current like the shunt regulators did. In this way, by simply interrupting the current, these types of regulators can control large amounts of current, 30, 50, 90 amps, perhaps even more. Because the current flow is stopped, there's no tremendous heat generated. So these types of regulators can be quite large. These types of systems, therefore, are used for larger currents, larger systems, and perhaps more complex systems as well, because they're larger. An example of a large series type of regulator would be this central type of controller that's often used in telecommunication systems. A lot of features are built into this regulator. We'll review those later. But the basic charge regulation regime that's built in is that series type of control. When the battery voltage rises to a set point that indicates it's full, the array current is opened up. A final or third type of regulator design is called a pulse width modulation type of charge controller. This involves more complex electronics. What's going on in this design is more of a continuous monitoring of battery voltage and current flow. Variable frequency pulses are allowed to flow from the module into the battery. When the battery is at a low state of charge, the pulses are quite long, perhaps even continuous. Lots of current can flow. As the battery voltage rises and the battery gets more full, the pulses become narrow and the delay between them becomes longer. So less and less current flows in over a period of time. There's different detailed configurations of these types of controllers. Some of these are shunting type, some are series type. But the point is, instead of waiting for a single set point to occur before some action is taken, there's a continuous variation in current flow, which is, in a sense, a little more efficient use of the energy generated from the module. An example of a pulse width modulation type of controller is this controller made by Siemens that involves a shunting in a pulse width modulation type of mode. Instead of relying on just one controller to control all of the current from your array, you may face a situation where your array is large enough so that you have to install individual charge regulating units. We can do this, and this leads to what we often call subarray switching type of control. Let's take a look at that for just a minute. In this configuration, you might have so many modules that you break them down into smaller subarrays, with each subarray connected to its own charge regulating unit. These individual charge regulating units don't have to be set to the exact same voltage set point. And they also don't have to be sophisticated tapering type of controllers. They can be simple single stage, open, closed series type of controllers. For example, if we look at let's say a 12 volt charging system, one regulator might be set at 13.8 volts, another one at 14.0, another one at 14.2, and so on, to gradually taper off each subarray's current flow, and finally lead with a very small amount of the full array trickling into the battery at the end. We could also have a situation where part of the array, as a subarray, is connected directly through a switch and a fuse to the battery. The reason for this might be a concern for lightning considerations or electronic failure of your charge regulators. If you have an extremely important load and you're concerned that perhaps there might be electronic failures with your charge regulators, you could have a portion of your array connected directly through safety switches and fuses to your battery, so that if the regulators were to fail, there'd still be a part of the array trickle charging your battery. One critical point: you've always got to make sure that the charge regulator is set to the proper end of charge voltage for the kind of battery you're going to choose. It's really important. I think it's even more important to have the proper set point. I think that's more important than worrying about which type of charge regulation you're using: pulse width modulation, series type, shunt type, and so on. The value of that cutoff point, the point at which you take your batteries to be charged, is a critical factor. We have differences in those factors depending on the type of battery that we're going to use. We can look at three general classes of lead-acid batteries: liquid electrolyte batteries, absorbed glass mat, and gel types of batteries. In these three cases, I've drawn out some very general recommendation numbers. You can't take these numbers to be hard and fast. Over years of dealing in this industry, I've talked to a lot of battery people, and I have never gotten real straight, clear answers on exactly how to set the set point. But in general, I think these guidelines are safe in terms of showing you the differences between the different types of batteries. Certainly what you notice is that the gelled and absorbed glass mat batteries should have lower set points than the flooded liquid electrolyte batteries. Typical values used for liquid flooded batteries might be 14.5, 14.7, 14.8 for a 12-volt battery. But for absorbed glass mat or gel batteries, should be reduced to 14.2, 14.1, perhaps even 14.0. I want to make one more point about the charge regulation set point and the different types of batteries we're talking about. One issue when we're dealing with charging batteries is we want to have a little bit of gassing at the end of each charging cycle for flooded liquid-type batteries. We need a little bit of gassing, not too much, in order to help mix up our electrolyte and make sure that we have uniform density of acid so we don't have stratification of our acid density. So that's one of the reasons why the voltage point is allowed to be set a little bit higher for flooded liquid batteries. For the sealed and absorbed glass mat types of batteries, we don't have to deal with a stratification problem. So we don't need and don't want
to allow gassing for those batteries. In fact, if those batteries do gas, the electrolyte loss, the water loss, is permanent. We can't simply replace it like we can with a flooded battery. So, once again, it's real critical to make sure that those set points are appropriate for the type of battery that you're going to use. One feature that might be included in charge regulating systems is a probe like this, an external temperature probe. This is for what we call temperature compensation. The external probe or internal probe measures the temperature of the battery itself and transmits that to the electronic controls in the charge regulator. The point is that as batteries get hot, the chemical reaction going on inside the battery is naturally going faster and further. We don't need to charge the batteries as much when they get hot. The contrast is true as well. As batteries get cold, the chemical reactions are going slower, and the reaction products are penetrating less into the active materials on the plate. We should take the charging process, at least the charging voltage, further. So, as batteries get hot, we want our voltage settings to be reduced, and as batteries get cold, we want our voltage settings to be set higher. The temperature compensation option will automatically do this for you. This feature is important for all types of batteries. It's especially important, though, for sealed types of batteries. The factor that's typically used is about minus 5 millivolts per degree C per battery cell, or about 30 millivolts per degree C for a 12-volt battery. The temperature probe can either be external to the charge regulator, as in this case, with a long dedicated wire and the probe itself taped onto the side of your battery, or in this case, another example of an external probe where we have a long cable and the probe that can actually clip on or tape on physically to the side of your battery. You can also have charge regulators with the temperature compensation probe and electronics built in, although that's not quite as accurate. It's perhaps sensing the ambient temperature around the regulator. That would be appropriate for only very small regulators. For large systems, the probe should always be external and physically attached to the battery. We can take a look graphically at this concept of temperature compensation and changing charging voltages. If we look at our graph that illustrates this negative 5 millivolts per degree C per cell sort of compensation, or negative 30 millivolts per degree C for a 12-volt battery, you can see that at 25 degrees, the standard rating temperature for most all processes, we perhaps have a voltage cutoff point of 14.5 volts. If the battery gets hotter, we want that voltage to go down. For example, if the battery rises to 40 degrees, we might be down around 14 volts. If the battery gets cold, then we want that voltage to be increased. We want it to take our charging process further because the chemical reaction is going too slow. For example, if the battery was all the way down to 10 degrees C, we might want our voltage even slightly above 15 volts. In this way, the charge regulator can automatically compensate for the fact that your battery needs a slightly different type of charge voltage depending on temperature. This is critical. I often run into people who think that temperature compensation is really an option, and it's often presented that way by regulator manufacturers. I consider the function to be important enough so that it shouldn't be an option. It's a mandatory option. Consider the problem. We often install our photovoltaic systems and our batteries in very hot climates. If we don't compensate that voltage point, we will consistently overcharge our batteries, right? And in an overcharging condition, we'll be losing electrolyte, possibly damaging the battery, shortening our life. Our systems won't be reliable. At the other extreme, we often have systems installed in very cold places. In those cases, the batteries need more voltage. If you don't have compensation, the batteries won't be charged enough. We'll install enough arrays according to our calculations, but our batteries simply won't achieve the charge point that they need, and the systems will fail as well. So temperature compensation is a real important option. I consider it mandatory in charge regulators. Let's talk for a minute about not using regulators at all. We've been talking about how important it is to protect your batteries from being overcharged, some of the other functions that they can perform. But let's stop for a minute and think about a type of scenario where you might have a module connected to a battery with no charge regulator. The circumstances for that are very narrow, and I want to be real clear that I don't advocate this type of system in a widespread type of application. There are certain application areas where it's appropriate, but let's talk about it for a minute. This sort of system design of putting a module connected directly to a battery with no regulator is what we call a self-regulating system. Be careful here. A lot of people often refer to a module used in that case as a self-regulating module. I don't like that terminology. That's dangerous because people think under any circumstances this module is a self-regulating module. I don't need a regulator. That's not true. It's real important to say a self-regulating system because that includes the environment as well as the module and battery. Everything has to be matched perfectly to have a self-regulating system. If any part of the system is not matched, you don't have a self-regulating system. The concept behind self-regulation has to do with our IV curve and how it responds to weather. Let's look at a couple of IV curves in Phoenix, Arizona in the U.S. where it gets pretty hot. Middle of the afternoon around 3 o'clock or so. We see the IV curves are compensated for lower light level because it's afternoon and for heat. The modules have gotten hot. We're comparing an M55 module that has 36 cells and an M65 module that has 30 cells. So there's a difference there of 6 cells, at least about 3 volts. Notice that what we're considering here is during the day, a battery voltage is rising. It's being charged up over time from the morning to the afternoon. So our battery voltage is rising because the battery's getting more full. What else is happening? The module voltage is falling. Modules are getting hotter. In the morning they start out cool. By the afternoon they're hot. So battery voltage is rising. Module voltage is falling. These two factors are countering one another. By the end of the afternoon we might have a situation as shown. If we look at the battery being charged up to about 14 volts, we can get almost 2 amps from an M55 module, whereas we're getting almost maybe a half of an amp from the M65. Why? Because the fall-off point of that curve has now moved into the range of our battery charging voltage for the M65, the self-regulating module. Whereas for the M55, a non-self-regulating module, it's still hanging out there with plenty enough voltage to give us almost full current. Some considerations that we've got to add into the equation of even considering a self-regulating idea are these. The load has to be used every day. Why? Because basically your system is out of control. You've deliberately designed a system to be, quote, out of control, unquote. You have no charge regulator to make sure that things are right. If you have a load that's operating every day, taking away from the battery just what the module puts in, the battery isn't going to be overcharged. But if, let's say, you have a cabin situation or some sort of system where the loads are used for a while and then vacated for days or weeks, with no regulator, that module is going to charge a battery to be full and then continue to charge an already full battery. It's going to be overcharged and damaged. And the other consideration is that the system, the environment, can't be too hot and it can't be too cold. I'm not being very precise. I'm sorry. The point is, I'm being general. In case the system, the environment, the module, gets too hot, the module was made with only 30 cells, barely enough to charge a battery under moderate conditions. If the module gets too hot, it won't have enough voltage to fully charge the battery under any circumstances. So your batteries won't be fully charged. If, on the other hand, you live in an extremely cold climate, that phenomena of the battery losing voltage and the operating point falling down the knee of the curve won't occur. So in cold conditions, a self-regulating module won't self-regulate. It'll overcharge the battery. So I'm being general in terms of my statements here. It can't be too hot. It can't be too cold. The load has to be used every day. The point is that a self-regulating system is a nice way to approach a low-cost, introductory, non-critical system. Typically something like a few lights, maybe a starter lighting kit for a remote home, maybe a small module connected directly to a large starting battery for a boat or an RV or a vehicle. That way it can gently trickle charge that battery and not really need a regulator. But for any kind of system that involves a large number of modules or important or critical loads, a self-regulating approach is not an appropriate approach for that system design. You should include a regulator to protect your battery. There might be some circumstances where you might not need a charge regulator. What would these circumstances be? It'd be a condition where the battery is large enough and the array is small enough so that even under peak conditions in the middle of the day when the sun is the brightest, the current flowing from the array into your battery is already at a slow enough rate so that there is not much gassing. It's effectively at the trickle charge rate that a charge regulator would take you to anyway. If the charge rate from the peak of in the peak of a day from your array is around the 100-hour rate or slower, that's already at a trickle charging rate. You're already relatively slow. You may not need a charge regulator under those circumstances. These circumstances are rare. It typically in large systems only occurs when you have 15 days or more of battery autonomy, because you've then got such a large battery that the array current flowing in is quite small. The way you can calculate whether you've got this situation or not is to calculate your peak charge rate. That's the battery capacity that you've installed divided by the peak array current. You calculate that by taking the number of batteries in parallel times the capacity of any one battery and dividing that by the number of modules in parallel times the max power current of a module. It's a rough calculation. And you'll get your charge rate. If that charge rate is equal to or less than the 100-hour rate, then you're in a situation where your battery bank is big enough, your array is small enough, and you can think about avoiding the cost, the possible complexity of installing a charge regulator. Under most circumstances, though, typical systems involve less than 15 days of autonomy, so the ratio is not going to work out. And under all those other circumstances, which is the vast majority of all systems, we need a charge regulator to prevent our batteries from being overcharged. We talked about different types of charge regulators, some of the different features involved, some of the set point features that you have to be careful about. Question comes to mind, how big of a regulator do I need? I don't mean physically, how big does it have to be, but how much current should it be designed to handle? Regulators are measured by their array current carrying capacity. Is it a 5 amp controller, 10 amp, 20, 30, 50, 90, and so on? For example, we might have a regulator as small as 3 amps, 5 amps, 10 amps, like this, 25 amps, as big as 30, 60, or 90 amps for larger controllers. So you need to be equipped with a simple equation that allows you to calculate the amount of current that you need to regulate. Then you look at literature or the products that are available. You say, I like one product or another. It can handle so much current. I'm going to need so many of those regulators. Or if you decide you want to use one regulator, choose one big enough to handle all the current that you're going to have to regulate. It's a simple calculation, but it involves an important factor. I want to make sure you include it. We have to size the regulator large enough in terms of current capacity so it can handle the expected current from the array under all circumstances. Remember, when we talked about the standard light level that's used by all manufacturers, 1,000 watts per square meter of light, we said that that measure is standard and can be measured on the Earth's surface, but it is possible to measure more than 1,000 watts per square meter. 1,100, 1,200, 1,250 is not unusual. Under those circumstances, if you had 1,200 watts per square meter, 1,250 watts per square meter shining on your module, your output in terms of current would be 25 or more % greater. You better size your charge regulator large enough to handle that circumstance, even if it's rare. This can be caused by reflective material in front of the module, white sand, white rock, snow cover, or white billowy clouds that might come and go. It can be a temporary situation, only for a few minutes, but if that current level is too high and stresses out your charge regulator, it can fail. And your whole system reliability is shot simply because you didn't oversize your regulator by a little bit. So I recommend that you apply a safety factor of at least 1.25. You can apply more if you want, but I think as a minimum standard, this is safe. In other words, you look at the amount of current that you would expect under normal circumstances, and then increase your current by at least 25%, and choose a regulator that can handle that level of current. Then you'll be safe. So the simple formula to use is the number of modules in parallel times the operating current of one module times a safety factor of 1.25. The operating current should be the max power current, IMP, for series types regulators, and ISC, or short circuit current, for shunting type regulators. Because when shunting regulators are operating, they're going to short circuit the array, and that much current is going to be flowing. Consult manufacturer's literature regarding this point, because they may say that a regulator is, let's say, a 30 amp regulator. Have they built in some extra headroom there that allows you to be safe or not? You don't know from the literature. So read carefully, and if it's not clear to you, consult the manufacturer. And if you're in any doubt that there's enough headroom built into that number, add your 25% factor. Let's use this particular charge control model as an example to illustrate some of the other charge controller functions that you might have available to you. Certainly, you can have temperature compensation with a probe connected to the regulator to modify the set points based on battery temperature. You might even be able to have adjustable charge voltage set points. In this case, for example, the set points are, the choices that are available to you are 15.3, 14.8, 14.3, and 13.8. That spans a range of all types of batteries, from gelled and absorbed electrolyte sealed batteries through flooded batteries and up to NiCad batteries. Some of the other functions that we might look at is low voltage alarm. That's handled in this area of this particular controller. The alarm points are adjustable. We have a visual indication of both a high and a low alarm situation. And we have relay contacts available both for the low voltage and high voltage situation. The relay would be involved in closing contacts, which would then perhaps operate an audible or visual alarm. Might even operate a transmitter that would transmit on an unused channel to a base station, indicating that either the batteries are undercharged or overcharged. Instead of simply sounding an alarm, we may want to actually operate a generator set to charge our batteries back up. In this particular design, we have generator start circuitry. The starting point is adjustable, and the contact points for starting the generator are indicated here. The set points that we might use for the low voltage alarm or the low voltage generator start conditions vary, but typically the values that we'd want to look at are anywhere between 11.8 and 11.5 volts for a typical 12-volt system. This corresponds to roughly about 60 or 70% state of charge for a battery. To be very precise, those voltage points should be current compensated, because as a battery is discharged, its voltage will depend on the rate at which it's discharged. But these general numbers that I've given you are a rough guideline just to give you a sense of where those voltage points might need to be. Instead of just looking at alarms and generator starting, we may actually want to consider disconnecting some non-essential loads if the batteries are getting too low. Certainly you don't have to do that if you have a standby generator. But if you don't, you may have some non-critical loads, some lights or fans and so on, that you can actually disconnect to protect your battery from being further discharged. In that case, this device has a load disconnect option built in. Again, it might be adjustable, and the loads that are connected directly to the controller would be the ones that are disconnected. If you had essential loads, those would be connected directly to your battery and would be unaffected by the circuitry. Also built into the general plan of the controller might be service disconnects or overvoltage protection, disconnects and circuit breakers for your array connections, your battery connections, and your load connections. And finally, you should have some sort of feedback to the user, some sort of visual display of at least voltage and perhaps current as well. It can be as simple as some LEDs or a simple meter that goes from green, yellow to red, or it might be as sophisticated as shown here with a digital display that might show battery voltage and array current and load current. Different types of regulator designs will involve different numbers of options. Whether you choose these options or not depends a lot on budget constraints, the particular client that you're trying to suit, the criticality of the load, other factors that you would weigh. But now we've taken a good look at the function of regulators, how they should be sized in your system, and some of the other functions that might make the complete aid that a charge regulator gives to a photovoltaic system. By way of summary then, we've looked at different regulator designs, different ways that the regulators can be installed in your system, ways to size your regulators so that there's enough capacity to handle the expected current and even current under bright conditions. And we looked at some of the functions that typical charge regulators or charge control systems can offer to your photovoltaic system design toolkit. In order to maximize the energy that we can transmit to our loads, there's a couple of tricks that we can play in photovoltaic system design. During this segment, we're going to look at two types of tricks, two types of technology that we can introduce to our system to enhance its performance, to either extract more energy from the sunlight that we have available and transmit that onto our loads, or given the energy that we get in our modules, how can we better match the transmission of that energy onto our loads? The two types of tracking mechanisms that we're going to look at are either sun position tracking mechanisms, which are mechanical in nature and actually move the module, or electronic maximum power tracking devices that are either solid-state devices that simply modify the transfer of energy. Let's focus first on sun position tracking as an enhancement to our system design. One of the first things that we have to examine when we're dealing with tracking the sun and the effect of angle on the performance of our system is what's the effect of tilting the modules up from horizontal. When we measure weather data, that's typically done using electronic devices that are mounted horizontally, flat. They capture the energy radiated by the sun in the summer and the winter. We can use computer programs to predict what that insolation would be on a tilted surface. We use those computer programs to tell us what's the optimum tilt angle up from horizontal that we should mount our modules at. So let's take a look at that first and examine what the effect might be of tilting our modules up to face the sun. Graphically, we can plot the insolation that we would receive on a tilted surface different times of the year. Pick the location for Los Angeles, and we're looking at the effect of tilting the modules up from horizontal. The flat data is the actual original data that we started with that's measured at weather stations. And you can see that it begins very low in the winter and peaks in the summer and falls back down again in the autumn and winter. As we begin to tilt our surface up from the horizontal, what happens to our insolation profile?
By tilting up, we're actually facing towards the low winter sun. We're starting to face away from the high summer sun. You can see the change in the profile. We begin to intercept more insolation in the winter months. The insolation goes up. The summer sun is passing above, perpendicular to our surface. We're actually capturing less of the insolation that's available from that summer sun. So our insolation available goes down. The tilt angle that we want to choose is going to depend on the load profile that we're trying to match. If we're trying to match up to a load that has a peak demand in the summer, we want to have our modules tilted to a low angle that favors the high summer sun. We don't have a heavy load in the winter, we don't care about that. If our load is heavy in the winter or is a fairly constant load, then we'll want to tilt our modules up from the horizontal so that that insulation profile is more flat and is more appropriately matched to our load profile. One aspect of positioning our modules is choosing the proper tilt. We can actually increase the amount of insulation that falls on a module at a certain tilt angle by tracking the sun east to west on its daily motion. We can also adjust that tilt angle from summer to winter as well if we want to. This can be accomplished by what we call a sun position tracker, a mechanical device that actually holds the modules and is the mounting structure. But instead of holding the modules at a rigid fixed tilt angle, now we either through passive solar techniques or active motorized techniques can move that surface east to west, just like a flower would track the sun. This model of a tracking device helps to illustrate what I'm talking about. Not only does the tracker hold modules at a desired tilt angle, but it would actually mechanically follow the sun during the day, east to west, and then reset itself either in the evening or the next morning so that it can catch the morning sun. In this way, it can capture a maximum amount of insulation that might be available on any particular day. Let's take a look graphically at the enhancement that we might get from tracking the sun east to west and perhaps adjusting seasonally. We can look at a typical insulation profile in a day. First, let's look at the profile from a fixed angled array. The insulation falling on the surface produces current. That current flow rises gradually, peaks in the middle of the day, and falls back down in the afternoon. By tracking the sun east to west in a single axis, we face the low-angled sun in the morning directly with the module. So we're intercepting more light, we generate more current. So at the same time in the morning, we're able to generate much more current. The current value rises quickly, stays high during the day. In the middle of the day, of course, the two are the same because they're both facing noontime sun. And then the profile stays high in the afternoon and finally falls off with the setting sun. The enhancement that we get is illustrated by the increased area on either side of the curve. Instead of just doing single-axis tracking, where we're following the sun on a daily basis, what if we also introduce some adjustments for summer and winter? That would depend, the enhancement would depend on which month. In this case, we're looking at the enhancement in June being a slight enhancement over single-axis tracking. If we look at the profile of our module output over a year, we can also look at the different enhancements that occur at different months. The amount of enhancement is going to depend drastically on the particular location, particular latitude, and so on of the site. If we look at the profile over a year, we can see that a fixed module has been put at an angle that gives a fairly constant output. If we track that sun east to west at that same tilt angle, we get some enhancement in the winter, a great deal of enhancement in the summer. That makes a lot of sense because in the winter, we're tracking a sun that's only up for a few hours. it's almost the same tracking that short winter sun or being fixed. So the enhancement isn't so great in the winter. In the summer, however, we have a large arc of sun movement that we can track, so we gain a lot more. So you see that extra enhancement in the summer. And you also see the added effect of adjustment for summer and winter, adding a little bit more to the output of the module. We can look at different tracking profiles for different locations around the world and see that the enhancements are slightly different depending again on particular weather conditions and particular latitudes. The other type of sun position tracker that we can talk about is a passive type of tracker. By that I mean it's not actually using any electricity from the module. It's simply using solar energy to move the module. This desktop model we have here is a small model of a different type of tracker, a passive tracker. The design of the tracker involves Freon tubes partially filled with oil and some shadow masks that partially shadow both tubes. As the sun moves throughout the day, a shadow is cast on one side and solar radiation falls on the other tube. That causes the freon to expand in the tube, pushing either oil to one side and displacing the tracker by weight, or we might have a different design that has two differential pistons, and the pressure difference between the two tubes causes a movement of the tracking surface. This type of tracker has to wait for a morning reset from the morning sun in order to find the sun in the morning. By way of summary then, we've looked at a certain type of enhancement to solar radiation coming into our system. Instead of having our modules just mounted at a fixed angle, we can have the modules track the position of the sun, either a single axis tracker moving east to west, or a double axis tracker that adjusts for summer and winter changes as well. Another type of tracking that we can look at is not physical tracking, but electronic tracking of our power. So now we're going to talk about an electronic device that takes the power that we receive from our modules, whether they're fixed or tilted or whatever, and tries to maximize the transfer of that power to our load. We call that a maximum power tracking device, or MPT. This is an example of a device that's used in water pumping systems. That's probably the best example where maximum power tracking gives enhancement to system performance. If we couple up solar modules to a DC motor directly, we can have system performance in a very simple and reliable way, but it's not a very efficient match. This max power tracking device enhances that match and increases the efficiency of that type of system. Let's take a look at what I mean by maximum power tracking. It again refers back to our IV curve. Let's look at the IV curve for a module early in the morning or late in the afternoon. In other words, in a condition where there's low insolation. This could also be a condition where there's a great deal of fog or overcast skies. In that case, we have our module potential performance curve, and we can isolate the maximum power point of that module under those conditions. We can also create a curve of constant power. So anywhere along this curve of constant power, we're also indicating the same amount of power we could get from the module. In other words, at approximately 16 volts in this case, we get approximately 1 amp. Well, at 8 volts, we get approximately 2 amps, and so on. We can now think about matching up our load curve, the curve from a DC motor, let's say, a DC water pump, to this now modified power curve. We no longer have to live with just the IV curve as a potential output. We can look at this inverted curve of constant power. The job of a maximum power tracking device is to take the DC input from a solar module or solar array and change that and match it to a DC load. Let's look at how that might happen. Again, we're looking at the same IV curve, the same time of day or the same overcast conditions that would give us a low IV curve. Let's look at the first condition of directly connecting a solar module to, let's say, a DC motor in a water pumping situation. That would be condition A, or point A. We have our motor curve, our load curve, intersecting our module output potential curve at point A. Very low voltage, very low current. This might even be a condition where there's so little current that the pump might simply be moving but not actually even pumping water. What happens now if we introduce a maximum power tracking device? We now have the module DC power going in at a certain voltage. And the electronic device can translate that into current and voltage at different settings. Let's look at points C and B. The electronic device operates the module at point C and translates that power along that curve of constant power, and now intercepts that motor load curve at point B. The enhancement is greater voltage and greater current. The pump is pumping faster, more water is flowing, perhaps starting earlier in the morning and continuing to pump later in the afternoon. So the enhancement now moves us from intersecting our curve and operating at point A to operating at point B. This kind of enhancement can drastically improve the amount of water that's available from a water pumping system. The improvement that might be typical from directly connecting to using a maximum power tracking device might be as much as 40 to 50% or even more. So in those cases, the added cost and perhaps the added complexity of a maximum power tracking device can be well warranted. So by way of conclusion, let's look at the two types of trackers that we've been talking about. They use the same word, tracking, but they're really quite different. I want to put them next to each other and compare them and see where they might be the best. Let me say by word of warning, both of these enhancements to our system performance involve added complexity. And my position from a module manufacturer is we make a product that is reliable from the beginning, no moving parts and so on. By introducing complex electronics or complex mechanical devices, we might be slightly compromising the reliability of our system. Now, maybe not. Maybe the devices are quite reliable. But my concern is watch out for seeking efficiency and compromising simplicity and reliability. But given the fact that I can gain so much more energy by tracking the sun or by matching my output to a motor, I'm very interested in looking at these types of enhancements. A sun position tracker maximizes the input into my system in the first place. By tracking the sun, I'm able to bring in more energy into my panels in the first place and transmit those onto my loads. An electronic maximum power tracker takes the power that I'm given on my module and tries to maximize the output to my loads. You see the difference between these two approaches. Sun tracking systems would be of great advantage when you have clear sky, and therefore not of great advantage when you have overcast sky conditions. The sky is very overcast, you don't have to track. It doesn't matter which way the modules face. Also, I wouldn't use tracking systems in situations of very high winds. It could be dangerous. It might possibly damage the tracker, although they're designed to handle pretty high winds. Electronic trackers would be good for sort of a complementary situation. They don't maximize input, but they maximize output to my DC motors and my water pumps. If I have conditions of low insulation due to overcast, cloudy skies or foggy skies, a sun tracking system won't give me the enhancement that a maximum power tracker will. Choosing a sun position tracker or an electronic tracker is ultimately the choice of a system designer. You've got to make a trade-off between the added cost and complexity of these devices and compare that to the expected gain in performance. But in conclusion, both of these are excellent means of enhancing and improving the output of our solar power systems.